Hi everyone. So now that we've finished with our exploration of the Fourier transform, one of the big applications that came out of that was the use of the transform in studying differential equations. And it should have been obvious that the Fourier transform is a powerful tool for studying differential equations, but really it's most suited for partial differential equations, where it's one of the core methods. If we're working in ordinary differential equations, we might want to look for a more straightforward tool to use where the computations are easier to perform and the structure of the transform is just more transparent. So for the last 2 weeks of the course, we're going to talk about maybe the most single popular tool for solving ordinary differential equations, which is called the Laplace transform. And the Laplace transform is widely used in conjunction with the Fourier transform in the study of physical systems. Many of you will have seen the Laplace transform in classes already. Typically, your first introduction to the Laplace transform is somebody tells you what it is, writes down the definition, gives you a table, and then you just practice doing it over and over and over again without not a lot of theory about where it comes from or the different areas that it can be applied in. The big thing that the Laplace transform brings to the table when you're studying ordinary differential equations is the ability to deal with forcing functions that are discontinuous. And not just discontinuous, but impulse type forcing functions, where you have some system that's oscillating and then you strike it. So that's sort of the big objective of what we're going to do with this. And we're going to start with what the definition of the Laplace transform is. So the Laplace transform is a transform, which means it takes in a function of one variable and produces a function of a different variable. And the idea with the transform is that if we can shift the domain that we're working in, we can make an easier problem to solve, and then hopefully we can shift back to recover the answer to our original question. So the definition of the Laplace transform is as follows. The typical letter that's used for this is script L. So the Laplace transform of f of t is defined to be the integral from 0 to infinity of f of t e to the minus st dt. And normally when we write down the Laplace transform, we need it to be the case that this integral converges. And so it's typically the case that this s up here, this power that controls this exponential, has to be a positive number, because if it's not positive, then e to the st blows up. So normally this comes with a condition that s is positive. Because this is an improper integral, there are going to be questions of convergence. When does this integral converge versus when does it not converge? For which f's do I have a well-defined operation here? It turns out to be the case that the easy or the rough way to understand that is, as long as f is sub-exponential as t goes to infinity. And what I mean is, since I'm taking f of t and I'm multiplying it by an exponential with a negative exponent, as long as f doesn't grow faster than an exponential decay, then this integral is going to converge. So we'll be more precise with that later, but for now it's enough to know that f could basically be any polynomial, any trig function, a lot of exponential functions. There's all kinds of things that you can stick into this. The second point is, even if you've seen this in a different class before, it just seems like a magic formula. We've just dropped it out of nowhere. Here you go. Here's the Laplace transform. It's this integral from 0 to infinity. It kind of looks like the Fourier transform, but it's only on half the domain. So go out and calculate some Laplace transforms. I always found that kind of unsatisfying, so I'd like to sort of try to give an idea of where this comes from and how natural the idea of the Laplace transform actually is. One of the big moves that we did when we were talking about the Fourier transform was we used the Fourier series to motivate the Fourier transform by thinking of the Fourier transform as the continuous version of the Fourier series. And it turns out to be the case that the Laplace transform is the continuous version of a discrete operation as well. So Laplace transforms arise naturally from thinking about power series, and that actually explains partly why they're so useful at solving differential equations. We can think about the Laplace transform as the continuous version of a power series. So what do I mean by that? What is a power series? That's right. The answer is a power series is actually a transform of a discrete function. You've probably never thought about it that way before, but that's what it is. What a power series does, what a power series actually does is it takes in an, which is a coefficient function, where n could be 0 or 1 or 2, Any non-negative integer that you give me, I plug in and it spits out a coefficient. So an is actually a function. It's a discrete function that takes integers in as its input and spits out coefficients as an output. And what a power series does is it evaluates those coefficients. It adds them up. And how does it do it? Well, it takes in an an and it pushes it into this machine where it attaches each an to a term x to the n. And then it adds them up into a function we can call a of x. So the function that comes out the other side is the a of x. So this is a transform. We come in with a function in terms of n, which tells me what the coefficient function is, and it comes out with a function of x. This is easier to see what's happening if I give you some examples. So what happens if my coefficient function an is just equal to 1? Well, if you take that an is equal to 1 for every single n, and you evaluate it inside of a power series, that means everywhere you put a 1, well, the sum 1x to the n is just 1 over 1 minus x, as long as x is less than 1 in absolute value. Well, this is exactly what I meant. We started with a coefficient function, we put it into a power series, we added it up, and we got a function not of n, but of x. So a power series is just a transform. Another common function is, what if I fed it 1 over n factorial? If I feed 1 over n factorial into the power series transform, well, I plug it in, 1 over n factorial x to the n, and that series adds up to e to the x. And e to the x is defined for all x. But the idea is the same, that I have a coefficient function, 1 over n factorial, and I fed it into the power series transform, and I added it all up, and what came out the other side was e to the x. So if I thought about the power series as a transform, in the same way that I thought about the Fourier series as a transform, maybe what we could do is think about what happens when the coefficient function is not a function of an integer, but a function of a continuous variable t. So what happens if a of t is a function of a continuous t? And of course, the t is going to be restricted to be from 0 to infinity, just like the n's were for the coefficients of a power series. Well, let me just write down the formula. Now I'm starting with a of t. A of t gets thrown into the power series transform. And how did we do that? Well, we took a of t and we multiplied it by x to the t. That's just like multiplying by x to the n. But now when I add up, I can't use a sum anymore because this is a continuous variable. But the continuous version of summation is integration. So I can integrate over all possible values of t. And this thing right here, this is the Laplace transform. It's not the same as the formula that I wrote down, but that's just a cosmetic change, which I'll show you how to do. This idea right here is where the Laplace transform comes from. It's literally the same exact idea as adding up a power series. But instead of putting in discrete coefficients, I have continuous coefficients. So this is some function, a of x. In the same way that the structure of the coefficients tells us whether or not a power series converges, the function a of t that we feed into the Laplace transform tells us whether or not this integral converges. Now, how do we get our standard Laplace transform equation from this expression right here? Well, I can just show you what the cosmetic changes are. So the first thing is, if we're thinking of a of t as our coefficients, and we feed it into this integral from 0 to infinity of at x to the t dt, which you should just be able to straightforwardly look at that and say, that's just the same as a power series. Now let's cover up all that intuition by hiding it in notation that's just computationally efficient. The first thing is, hardly anybody calls a function a of t. F is the letter that we normally use for functions. So the first change is we're going to write f of t goes to the integral from 0 to infinity of f of t x to the d tt. Now I've not changed anything here. Cosmetic change. The second change is x to the t is kind of nasty to take a derivative of. Because if I do that, I'm going to end up with natural logs running around. And, natural logs of x are nasty. So let's not do that. I don't want to integrate or differentiate x to the t. I'd really prefer there to be an e down there. So what we're going to do is we're going to rewrite x as e to the natural log of x. So I can always do that. So I can replace x with e to the natural log of x. So now we're getting closer to what the actual Laplace transform definition looks like. So now we're sending f of t, and we're throwing it into the integral 0 to infinity of f of t e to the natural log of x times t dt. Okay, now what? Well, in order for this integral to converge, it had better be the case that this x right here is between 0 and 1. After all, if it's bigger than 1, like 2 to the t, that blows up as t goes to infinity. Because remember, the t values are going to infinity because those are the limits of integration. So I need x to be between 0 and 1 for this integral to make any sense, or to have any hope of making any sense. So if x is stuck between 0 and 1, then that means the natural log of x is stuck between 0 and minus infinity. So I want to characterize this integral with a positive number s, but in order to do that, I'm going to have to do a substitution that involves the negative sign. So if the natural log of x is a negative number, then maybe what I could do is I could make the substitution minus s is equal to the natural log of x. Because if I do that, then s will be a positive number. Natural log is negative, minus s is positive. And now we've got it. This is the Fourier transform. F of t is the transformation, the integral from 0 to infinity, f of t e to the minus st dt. And that right there, that's the Laplace transform. So the Laplace transform is just the continuous version of a power series. If we let the coefficients of a power series become a continuous function, it's the Laplace transform. L of f is equal to the integral from 0 to infinity of f of t e to the minus st dt. Just like a power series. But a lot of times when we're doing computations, it's actually more convenient to write capital F of s. So capital F is the transform of lowercase f. And the variable has to change because we're replacing the variable t with the variable s. And you could think of the variable s as sort of being like a frequency domain variable. The Laplace transform and the Fourier transform are actually related to each other. It's obvious because you've got integral from 0 to infinity, you've got this exponential running around in here. But s doesn't quite map to frequency directly in the way that it does in the Fourier transform case. But it gets referred to as either the Laplace domain or the frequency domain, even though s isn't really a frequency in the way we thought of before. So it's still okay to think about s is frequency. Because whatever we're doing here, we're leaving the time domain and we're entering some other domain, the Laplace variable. The usual approach at this point is to start computing the Laplace transform of a bunch of functions. And then somewhere, 2 or 3 lessons down the road, we talk about why we're doing all this. I want to motivate why we're using this to solve differential equations right out of the gate. Even though we can't be quite precise technically, at least I want to show you why the Laplace transform is so appealing as a tool for working with differential equations. And so what we're going to do is, the very first Laplace transform we're going to compute is the Laplace transform of f prime. Now in the Fourier transform case, remember that the Fourier transform of f prime was equal to 2 pi is Fourier transform of f. And we're really hoping that we get the same kind of rule when we're working with the Laplace transform. Because if I have that same kind of rule, then I could do the same thing. I could plug in derivatives and I could reduce the function just to Laplace transforms of the original function. The power of the derivative property of the Fourier transform is that the Fourier transform of the original function shows up in the formula for the derivative. So to motivate even studying the Laplace transform at all, I want to write down what the derivation of the Laplace transform of the derivative is. So why use the Laplace transform? Why use L of f to study ODEs? And the answer is the Laplace transform of f prime is equal to the integral from 0 to infinity of f prime of t e to the minus st dt. In the same way in the Fourier transform, what we did was we used integration by parts to come up with a formula for this. I'm going to use integration by parts here. If u is equal to, let's say, what do I want to take the derivative of? E to the minus st. That's what we need to do here. I take the derivative, and I'm going to get minus s e to the minus st. So dv will be f prime, because if I integrate f prime, I get f. So now applying what we've derived here from the integration by parts, we're going to get that this integral is equal to u times v, which is f e to the minus st, evaluated from 0 to infinity, minus the integral of v du, which will be plus the integral from 0 to infinity of s f of t e to the minus st dt. Now this integral over here, if I put in infinity, if I take a limit as I go to infinity, this part will go to 0 because e to the infinity is nothing. And let's just assume that f is sub-exponential in its growth so that this transform exists. Okay. Then if I put in 0, e to the 0 is 1, and f of 0 is f of 0. So all of this turns into minus f of 0. And this is s times the integral from 0 to infinity of f e to the minus st dt, but this is the Laplace transform of f. So what you get out of the formula in the end is s times f of s minus f of 0. So that is, I've encoded in the Laplace transform of the derivative, the Laplace transform of the original function and the initial condition of that original function. So what we've shown is that if the Laplace transform of f is written as capital F of s, then the Laplace transform of f prime is equal to s times f of s minus little f of 0. That is, the Laplace transform of derivatives is incredibly useful because we get a reduction to the original function, the Laplace transform of the original function. So the derivatives disappear and they turn into multiplication by the variable s. Now, there's a higher order version of this formula that we're going to go through when we get to the derivative section, but the same rule will hold for any number of derivatives. You're going to get a structure exactly like this. Okay, so that's motivation for why we're doing this. Laplace transforms play nice with derivatives. All right, so now let's compute the Laplace transform of some basic functions and see if we can figure out some patterns that we can work with. So what are some typical functions that we see when we're working with differential equations? Well, polynomials are a good place to start. So what is the Laplace transform of 1? So this is just something you can do directly from the definition. The Laplace transform of 1 is the integral from 0 to infinity of e to the minus st dt. There's a 1 right here because that's the f. Integrating that, you get minus 1 over s e to the minus st evaluated from 0 to infinity, which is really secretly the limit as n goes to infinity of minus 1 over s e to the minus st evaluated from 0 to n. If you put an n in, e to the minus st goes to 0, so that term disappears. You put in the 0, and what comes out of this is 1 over s. So the Laplace transform of 1 is 1 over s. The Laplace transform of t well, again, integration by parts, and yes, we're going to be doing quite a bit of integration by parts in here. For this particular section, when you're computing directly with the definition of the Laplace transform, there's going to be a lot of cases where integration by parts turns out to be a thing that you need to be able to do. The other thing you could do is actually just consult a table of known integrals and just write the antiderivative down and evaluate it. In this case, if I do integration by parts, I'm going to get, let's see, here's u and dv, t1, 0, e to the minus st minus 1 over s e to the minus st, 1 over s squared e to the minus st, plus and minus, And so this thing turns into minus t over s e to the minus st minus 1 over s squared e to the minus st, all evaluated from 0 to infinity, which again is a limit. So this is the limit as n goes to infinity of minus n over s e to the minus nt minus 1 over s squared e to the minus nt minus 0 minus 1 over s squared. And it should not shock you that when n goes to infinity, that term goes to 0, and n does not grow fast enough to counter it. So n times an exponential that's collapsing to nothing is, the n is going to lose badly. And here, that goes to 0. All of this just turns into 1 over s squared. So the Laplace transform of t is 1 over s squared. There's actually a pattern here. So if the Laplace transform of 1 is 1 over s, and the Laplace transform of t is 1 over s squared, the pattern we're going to show here is that the Laplace transform generally of t to the n is equal to n factorial over s to the n plus 1. And you can see that right here. So we've shown these two cases. The t to the n case is something that we're going to do as an exercise. All right, well, that's good. So we can Laplace transform polynomials really easily, as long as the Laplace transform is linear, so I can spread it out over a polynomial. That's important to keep in mind, and we'll come back to that. This only tells us that we can work term by term. It doesn't tell us anything about spreading it out over a combination of functions. One more very common computation is that the Laplace transform of e to the at. This is actually really easy because now we're going to have exponentials combining. E to the at, e to the minus st dt, integral from 0 to infinity of e to the minus s minus a t dt. So it's typical to write this in this form, that we have to sort this out so that I want to explicitly write this as a negative exponent, because that's going to tell me something about what the sign of s minus a has to be. If this integral is going to converge, it had better be the case that s minus a is positive, because otherwise this exponent is going to be a negative. If that's not positive, then you're going to end up with a positive exponent and the whole thing is going to go to hell. Okay, so s minus a has to be positive in order to force the exponent to be negative. Now, if you evaluate this, you end up with minus 1 over s minus a e to the minus s minus at evaluated from 0 to infinity. The typical limit argument is going to get you that this is equal to 1 over s minus a. Okay. So that's the Laplace transform of some basic functions. There will be more in the exercises for you to do by hand. It's more typical when you're working with these things in practice to work with a table, and we'll get there as well. The last property that I want to talk about right now with the Laplace transform in this introductory lesson is the fact that the Laplace transform is a linear operation. And what I mean by that is, if I took the Laplace transform of a sum, then it turns into the Laplace transform, or the sum of the Laplace transforms. And that's very easy to show because the Laplace transform of f plus g is the integral from 0 to infinity of f plus g e to the minus st dt, but then that splits up into an integral of the Laplace transform of f plus an integral of the Laplace transform of g, right? So the Laplace transform respects sums. You can put a sum in and it turns into a sum on the output side. Likewise, the Laplace transform of a constant times a function is just going to be equal to that constant times the Laplace transform of the function. And we want this property to be true because this is the same property that makes integration and differentiation so useful. That if I have a Laplace transform of a linear combination of things, I can apply it to each individual piece. So for example, the Laplace transform of 2x squared minus 3x plus 1 is equal to 2 times the Laplace transform of x squared minus 3 times the Laplace transform of x plus 1 times the Laplace transform of 1, if we're thinking of x as the independent variable and not t. The Laplace transform is still going to produce functions in the s domain, regardless of what the input variable is. And what we're going to get here is 2 times 2 factorial over s to the third because of the formula that says that the Laplace transform of t to the n is equal to n factorial over s to the n plus 1 minus 3 times 1 factorial over s squared plus 1 times 1 over s. And so I can compute Laplace transforms of combinations just by applying it term by term. So that's a basic introduction to the properties of the Laplace transform, how you compute it for specific functions, and we're going to go into more complicated properties in the next part. But the core ideas that we've covered here are that the Laplace transform is easy to compute for basic functions. So YL. And the answer is it's easy to compute for basic functions. It plays nice with derivatives. And it's linear. All right. So I'll see you for the next video where we'll delve into some of the deeper properties of the Laplace transform. Take care.